So today, our speaker for today is Vishwa Dewage from Baton Rouge, the student of Getzer Olofsson. She will speak about Toplitz operator with quasi-radial symbol on the Fock space. Please, Vishwa.
Thank you for the invitation. So this is a joint work with my advisor, Professor Olofsson. Oh, okay. Okay, so first I will go through the basic definitions, and then I will introduce Toplitz operators with quasi-radial symbols, and then we'll diagonalize the Toplitz operators. And finally, we will talk about the C-star algebra generated by these Toplitz operators. So we start with the Gaussian measure on n-dimensional complex plane. We define it by d lambda nc equal to 1 over pi to the n e to the negative absolute value of c squared dc. And here dc is the Lebesgue measure on the complex plane. And we define the Fock space FCN by the intersection of the L2 space with the Gaussian measure and the holomorphic functions on Cn. And this space is a closed subspace of the L2 space. It is a reproducing kernel Hilbert space with the reproducing kernel kwc equal to e to the wc bar. And we also denote it by k sub c w. And for any c in Cn and for any function in the Fock space, the point evaluation is given by the inner product between f and k sub c. Now, the Fock space is a closed subspace of the L2 space. So we have the projection, and we call it the Bergman projection, and it's defined by so p f evaluated at c equal to the same inner product. Now, f is just a function in L2.
I would rather call this projection like Bergman projection.
Okay, okay, maybe I made a mistake here. Yeah, okay. Okay, now we are going to define Toplitz operators. So given a function phi, which is essentially bounded on Cn, we define the Toplitz operator T phi going from the Fock space to the Fock space with symbol phi by T phi f evaluated at C equal to the projection of phi f evaluated at C. So we are multiplying the function by the symbol. It's in L2 space, but not necessarily in the Fock space. So we take the projection. And as we noticed, the Bergman projection is given by the inner product between phi f and the reproducing kernel, and it's just this integral. So the Toplitz operator with symbol phi is a bounded operator with norm less than or equal to the subnorm of the symbol. And we are interested in the C-star algebra created by these Toplitz operators. And if we look at all the symbols which are essentially bounded, and if we consider the C-star algebra generated by those Toplitz operators, it's not necessarily commutative, but sometimes when we restrict the class of symbols, we find commutative C-star algebras generated by those Toplitz operators. Okay, so the way we restrict the class of symbols is through a group action. So suppose a group G is acting on Cn, and then G induces an action on the symbols by, so if A is an element of G, A dot phi of C, we can define it by phi of A inverse C, where C is in Cn, and this gives us a group action on the symbols. And we say a function phi is in G invariant if A dot phi is equal to phi for all the elements in the group. Now, we denote the space of essentially bounded G-invariant functions by L infinity Cn G, and the C-star algebra generated by those Toplitz operators with symbols in here by Tg. Okay. Okay, I'm sorry. Okay. Okay, so now we introduce Toplitz operators with radial symbols. So the unitary group acts on Cn, and that induces an action on the symbols, and we can consider the class of symbols which are invariant under the action of unitary group, and those we call the radial symbols. And the Toplitz algebra, the corresponding Toplitz algebra is commutative. And from this paper by Grudzki and Vasilevsky, the eigenvalue sequences of radial Toplitz operators on the one-dimensional Fock space are of the form gamma 1 am equal to 1 over m factorial times the integral from 0 to infinity a of root r to the m e to the r dr. Now, from this paper by Esmeral and Maximenko, the corresponding C-star algebra is isometrically isomorphic to the C-star algebra of C-star algebra CBU of square root slowly oscillating sequences. So this space is nothing but bounded sequences on n naught, which are uniformly continuous with respect to the square root metric. So I think a student of Professor Vasilevsky and Professor Vasilevsky also showed a similar formula for the n-dimensional Fock space. Okay. Okay, so now we are going to define what Toplitz operators with quasi-radial symbols are. So we are going to start with a k-tuple n, which we may also denote by n of k, and we will write n as the sum of n1 up to nk, and we can identify Cn as Cn1 cross up to Cnk. So any z in Cn can be recognized with this guy in Cn, where n here is the k-tuple. So these Cj's are in Cnj's. Now we look at the group G, which is the product of these unitary groups un1 up to unk. So un1 is the unitary group for Cn1 and so on. And Gx on phi defined by the usual action, which is also equal to the action on the components, because the group G is now the product of these unitary groups. So any element in here is also an element in UN, which we can identify these block diagonal matrices. So that's how this action works, and it's also equal to the action on the components. So we call these the symbols which are invariant under this group action, we call them quasi-radial symbols, and we are interested in the C-star algebra Tg corresponding to these symbols, the quasi-radial symbols. Okay. Now, so this, our group always depend on the k-tuple that we pick. So if k is equal to 1, we get the group un, so the radial symbols. So if we have just one component, it's gonna be just the radial symbols. And if k is equal to n, then the only way we can write the tuple is by writing ones. So that gives us the separately radial symbols. Okay. Now, so we can classify these quasi-radial symbols. So we have this lemma. So this is a well-known lemma which says the measurable function phi going from Cn to C is un invariant if and only if there exists a function a going from r plus to c such that phi of c is equal to a of absolute value of c. So the function phi is un invariant if and only if it depends only on the length of c. So similarly so this is for radial symbols. Similarly, we have a similar lemma for quasi-radial symbols. Now, for quasi-radial symbols, we have a product of unitary groups. So we get the measurable function phi going from Cn to C is G invariant if and only if there exists a going from R plus K to C such that phi of C equal to a of all the lengths of the components. Okay, so now our goal is to diagonalize the Toplitz operators with quasi-radial symbols. For that, the first step is to look for a representation that commute with the Toplitz operators. So now for the radial case, we have, so if we look at the group UN, we have the regular action of the group UN on L2 defined by pi n of A acting on F evaluated at C equal to F of A inverse C. Now the Fock space is invariant under this group action, so we get a representation acting on the Fock space by the same formula. And so the Fock space can be decomposed into invariant, so irreducible subspaces like this, where these PMs are homogeneous polynomials of degree n. So this gives us irreducible sub-representations of the regular representation of UN. So this is a fact from representation theory, and one of the references is this book by Goodman and Waller. Okay, now in our case, we have n equal to n1 plus up to nk, and our group G is un1 times up to unk, and the Fock space can be written as the tensor product of these Fock spaces with respect to our decomposition. Now, for each of these unitary groups, we have the representation that we discussed earlier, and we can consider the tensor product of these representations acting on this group, and it's given by the tensor product of each of the, so tensor product of pi n1 a1 tensor up to pi nk ak. And so as before, the Fock space can be decomposed now into these tensor products of the spaces of homogeneous polynomials. So, and in addition, our Toplitz operators, the Toplitz operators with quasi-radial symbols intertwines with this representation for all phi. So by Schu's lemma, we get that T phi restricted to any of these spaces is constant times identity. So here we denote the constant by gamma n phi of M. So M here is this K tuple, which denote the sequence of degrees of the polynomial spaces. And n is just the k tuple we fixed for the group. Okay, now, so we already diagonalized the Toplitz operators. Now we just have to find what the constant is. So as before, so we said that we can always identify this phi with an A defined on R plus K. So we can also identify the eigenvalue function with, so instead of writing phi here, we can write A. Now the formula for the eigenvalue function is given by this. So we have 1 over n plus m minus 1 factorial. So these are k tuples. And here we have the symbol which we identify by A. And root R here is just taking roots of each of the components, and R to the n plus m minus 1 here is just we take the we take Ri raised to the power mi plus ni minus 1 and take the product.
One question, Mi.
Yeah.
For this, you may do a very simple trick. I don't know how to prove this lemma, but you can consider just orthonormal basis in the Fock space, and then substitute, calculate the action of a Toplitz operator, and get this formula, or you do something another.
Yeah, so we are using orthonormal basis in a sense. Yeah, we are using it. Maybe a little differently, but yeah, the main idea is to use that. Okay. So now if you look at this formula, so if you look at the case for 1, that means when we have n is equal to k, that means the separately radial k. When we have the tuple of 1s, what we get here is just m factorial here and m here, because 1 cancels with 1. So we can write gamma n(a) of m as gamma 1(a) of m plus n minus 1. So this observation is important to reduce the problem later on. So it's all about just the separately radial case. Okay, now, in addition, we can clearly see that the Toplitz of algebra is commutative, because these eigenvalue functions are bounded functions on n naught k. So the algebra generated by that is commutative. Okay, so now we are going to prove the formula. So for that, we need this lemma. So if we take a homogeneous polynomial Pn of degree m, and if we restrict it to the sphere and take the L2 norm, it's going to be equal to gamma n divided by gamma of m plus n times the usual L2 norm of the polynomial squared. And in particular, if we take a normalized monomial Q alpha of degree m, it's got the L2 norm on the sphere of Q alpha squared is going to be just this guy, because when you normalize it, this guy is just 1. Now, we are going to consider this monomial Q alpha c, which is defined by the product of Q alpha I Ci, where cube alpha i's are taken from PMI's, and so Ci is just in Cni here. Then this product is gonna be in this tensor product of homogeneous polynomials. Okay, now we are going to compute the constant. So now Q alpha is the monomial that we consider here. Then, so T phi of Q alpha is just gamma in A M times Q alpha. So we can take it out, and norm of Q alpha is just 1. And this is also equal to phi of Q alpha in a product. And it's gonna be just this integral. And then what we do is we integrate separately on each of these spaces, and we replace phi by A, and then we take, apply polar coordinates to each of the spaces. So this doesn't depend on, this depends only on R, and we get from here Rj to the power 2mj, and this part we get from the polar coordinates formula, and e to the negative Rj squared we get from here, and the only spherical part we get is from here, and that's just gonna be the product of these normalized monomials restricted to the sphere norm squared. And this we computed from the previous lemma to be gamma of n divided by gamma of n plus 1, and we can use that. So our formula becomes just this, and then we use a change of variable. We send R to root R, and we get the final formula. Okay. So now we are done with computing the formula. So now we are going to talk about the algebra, sister algebra generated by these eigenvalue functions. So for that, we will start with this space CBU n naught k rho k. So we consider this metric rho k defined by, so now it's defined on n naught k cross n naught k. So we just let it be the sum of root mi minus root mi primes, or this sum, and we can use maybe an equivalent metric if we wanted to as well. And we denote by CBU n naught k rho k. This is the algebra of all bounded functions on n naught k that are uniformly continuous with respect to this metric, which we call the square root metric. Okay, now, so we are going to prove that the set of all eigenvalue functions, Gn, is a dense subset of CBU n naught k rho k. And in addition, we get that the Toplitz algebra is isometrically isomorphic to this is the algebra. Okay, so from the one-dimensional paper by Esmeralda and Maximenko, we have this inequality. So r to the power m divided by m factorial. This is the kernel for the formula. So this minus rm prime divided by m prime absolute value times e to the negative r integrated from 0 to infinity is bounded by 2 times this constant times absolute value of root m minus root m prime. And also, so this is just a gamma function. So this part is just a gamma function, which gives you m factorial, which cancels with m factorial, and you get just 1. So So first of all, we need to show that the set of eigenvalue sequences is contained in this algebra. So for that, we are going to use these two facts. So we are actually going to prove that the eigenvalue functions are Lipschitz with respect to the square root metric. So definitely they are going to be uniformly continuous with respect to the metric. So to prove this, what we do is we pull out the sup norm, and then we would be left with something like this. But instead of the one-dimensional case, we will have k-tuples here. So they're going to be products of things like this. And we can do our usual trick of subtracting a term and adding a term, and then applying the triangle inequality, and using this inequality and this fact, we get this constant times the metric. So this proves that the set of eigenvalue functions is a subset of CBU and not K rho K. Okay. Now we have to show the density. So before we show the density, we are going to reduce the problem to the separately radial case. So for that, so now our eigenvalue functions are not sequences, but we can still define left and right shift with respect to a k-tuple. So if we take a k-tuple S1 up to Sk, we can define the left shift with respect to S applied to the function on n naught k by, so left shift of sigma evaluated at m is just sigma of m plus s, and the right shift is just defined by sigma of m minus s if all the if mi is greater than or equal to si for all I and 0 otherwise for all m's. Now, so now we have that if sigma is in CBU, and if we take any k-tuple, and if we take left shifts and right shifts of sigma with respect to this k-tuple, they're still gonna be in CBU. It's because, so to make the square root metric small, so if we just take two natural numbers, and if we consider the square root metric of applied to those two natural numbers, to make that small, we have to make those two numbers really large. So square root oscillating with respect to the square root metric is actually a property in the tail end. So it doesn't really matter if we shift it to the left or right. Okay, and so we made this observation earlier that gamma NA of m is equal to gamma 1A of m plus n minus 1. So this is the general case. This is the separately radial case. Now this means gamma NA of m is just what we get when you apply a left shift with respect to n minus 1 to gamma 1A, the separately radial eigenvalue function. Okay, so using these two facts, we get that if G1 is dense in CBU, then so is Gn. So if the separately radial case is dense in CBU, then Gn is dense in CBU as well. So it's an if and only if statement. So if we can show that the separately radial eigenvalue functions are dense in CBU, we are done. Okay. Now, so we start with this. Now we try to show the density of G1 in CBU, and we start with this proposition. So if sigma is in CBU, and if epsilon is greater than 0, there exists a symbol and n such that for all m in n naught k with all the mi's greater than n, sigma m minus gamma 1 am is less than epsilon. So this proposition is kind of a generalization of the proof for one dimension, which was done by Esmeralda and Maximenko. So now if we define this set Kn to be all the m's in n naught k such that at least one of the mi's is less than n, then what this proposition is telling us is there exists n such that sigma minus gamma 1a restricted to Kn complement, and if we take the subnorm, it's gonna be less than epsilon. Okay, now if we look at the picture of this set Kn, so just for 2 dimension, the set Kn is something like this and Kn complement is something like this. And the previous proposition let us control this part of the sequence, the function. And so now, if you look at sigma minus gamma 1 a plus b subnorm, we can write sigma as sigma restricted to Kn and sigma restricted to Kn complement. And when you have sum of symbols, we can, that's eigenvalue sequence with sum of symbols is the sum of the eigenvalue sequence with symbols separately. And we can then decompose this as restricted to Kn and restricted to Kn complement, and we can keep it like this, and then we can apply the triangle inequality. So the part that we get here is the part that's controlled by the previous proposition, and if we can control this part, we are done. So with that proposition, if we can get that when we restrict a function in CBU to Kn, if we can control that, approximate that as well, then we are done, because the previous proposition let us control something like this. Okay. Now we are going to prove the, we are going to discuss the proof of this proposition. So now the proof is, so we are starting with a function in CBU, and we need to find a symbol n and a. So here we have, so we need a symbol and an n such that sigma minus gamma 1a restricted to Kn complement is controlled. Okay, so first we extend sigma to a function on R plus K, which is also uniformly continuous with respect to the square root metric. And we also need to keep the subnorms the same. And then we define the function gx by sigma tilde x squared. So sigma tilde is the extended function. And then this is going to be in CBU RK in the usual sense. So it's going to be uniformly continuous in the usual sense. And so we have this result. So if we look at the heat kernel H, we have that H star B, where B is just a essentially bounded function. This set is dense in CBU RK. So this can be taken as a consequence of Wiener's density theorem, or we can prove this using an approximate identity constructed using Schwarz functions. So because of that, and G is in CBU, so we can we get h star b minus g subnorm is less than epsilon over 3 for some symbol b. So for some function b in L infinity Rk. And then we let a be the be restricted to r plus k. So this is going to be our candidate for symbol. And so then we have this result. There exists n1 such that for all xi is greater than n1, h star a x minus h star b absolute value is less than epsilon over 3. So this connects a to b, and b is connected to sigma through this. Okay. And so the reason that we take consider the heat kernel is because we have this result which says there is n naught such that for all mi greater than n2, gamma 1 am minus h star a absolute value is less than epsilon over 3. So this connects the eigenvalue functions to convolutions with h. So now we have the candidate for this symbol, and we can pick n to be the biggest one of n1 and n2, and we put these three inequalities together and we get the result. Okay, now what's left is to control this part. So when we restrict a sequence to a set like this, if we can approximate it by an eigenvalue sequence, we are done. So we are not gonna do it generally, but if we assume G1 k minus 1 is dense in CBU, then we can prove if sigma is in CBU and epsilon greater than 0, then for all n, there is such that sigma restricted to kn minus eigenvalue function corresponding to A subnorm is less than epsilon. So we are not proving without this. So we have to assume this to control this part. Okay, now so we'll discuss the proof of this lemma later. And with this lemma and the previous proposition, we get the density of G1 in CBU. So the proof is simple. It's by induction on K. So when K is equal to 1, we have the result from Esmeralda and Maximenko, and then we just use induction on K along with this lemma. We get to prove the density of G1 in CBU and not K. Okay, so now what's left is to prove the lemma. Okay, so first I'm gonna discuss just the proof for dimension 2. So we want to, again, so we are going to assume the density for k minus 1, and we take sigma in CBU, and we let epsilon greater than 0, and we need to find a symbol such that sigma restricted to kn can be approximated by an eigenvalue function. So first we start with, so first we fix one of the variables, then this is going to be in CBU n naught. So sigma is in CBU n naught 2, but if we fix a variable, we get that it's in CBU n naught. Then because the density for one dimension is already proved, and we are assuming in the lemma, we get that the subnorm of sigma dot m naught minus gamma 1a is less than epsilon over 2 for some symbol a. Now, so if we consider just the sequence which has support only at m naught, like characteristic function at m naught, it's also clearly in CBU n naught. So we can also find a symbol such that the subnorm of the difference is less than epsilon over 2 times subnorm of a, where a is the symbol that we found here. Now, so these are all just one variable eigenvalue functions. So, and these are one variable functions. So we define this two variable function C x1, x2 equal to a of x1 times b of x2. And if you look at the eigenvalue function with this symbol, it's gonna be gamma 1a of m1 and gamma 1b of m2. Okay, now if we look at sigma restricted to, so this is the set km naught, sigma restricted to km naught evaluated at m1, m2 minus gamma 1c evaluated at m1, m2 absolute value. So we can, so this is the product of gamma 1a m1 and gamma 1b m2, and we can subtract this term gamma 1a m1 chi m naught m2 and add that, and we are left with this 2, and we are using triangle inequality. And if you look at this part, this is a common factor for both terms, which we can pull out, which is bounded by 1, and sigma of m1 m naught minus gamma 1a m1 is bounded by the subnorm, so less than epsilon over 2. And here, this is a common factor which is bounded by subnorm of the symbol. And we have chi m naught m2 gamma 1b m2, which is less than the subnorm, which is less than epsilon over 2 times subnorm of a. So altogether, we control this guy by epsilon, and this is true for all m1, m2. So we have the control for controlling subnorm actually. So we have sigma restricted to km naught. So the km naught is this line minus gamma 1c subnorm is less than epsilon. So the set k, so we only considered this line as of yet. Now the set kn is this guy, and it contains n many lines of lines like this and n many lines like this. And we can even control sigma restricted to k tilde j the same way. So we can write sigma restricted to kn as sum going from 1 to n, sigma restricted to ki plus sigma restricted to k tilde I. So from this, so each of these guys can be controlled, approximated by eigenvalue functions, and we get a bunch of eigenvalue functions, and some of them is again an eigenvalue function. So we are done. Now for the general proof, so we did the proof only for the 2 dimension. For the general proof, what changes is, so earlier, when we fixed one of the variables that was just in CBU n naught, Now, in the general case, when we restrict one variable, that's going to be in CBU and not k minus 1. And that's why we need to assume the density for k minus 1. And sigma restricted to kn is going to be in the algebraic tensor product of CBU and not k minus 1 and CBU and not. So this will take care of the general proof. Okay, so that's all I have. Thank you for listening. And do you have any questions?
Yes, please. Question and comments. Who will start? Igor.
And this is some, here are some references.
Well, I have heard this talk in Louisiana University, so I like your ideas. You have many non-trivial ideas, and I have to mention that jointly with Kevin Esmeral, we fought. We have fought in this direction, but we had a wrong idea that the resulting sister algebra should be the tensor product of the one-dimensional algebras, and it is not so. You found the correct answer. I like your lemma on the page 21. Could you please? 21.
20.
Next one. Yeah, this one. This one, the approximation of the characteristic function. Well, now you use our non-constructive proof, yeah? But this form of lemma is very attractive. Maybe you will be able to prove it by some constructive approximation.
Yeah, I tried to prove it constructively, but it looked very hard, and I was not able to do it.
Yeah, but I think this is a step in a good direction to think about one characteristic function. Yeah.
Okay.
So I'm very glad that you have solved this problem. Yeah.
Okay, thank you.
Other question or comments? Well, I have a question to you. We are in May right now. You are planning to finish your PhD next May.
Yeah.
So you have 1 year.
Yeah.
What are your plans for this year? How would you like to complement what is already done?
So, we are looking at so certain subgroups of metaplectic group and invariance under that. So we are actually looking at R plus SON. So we have the SON action by just the usual regular representation. And we are looking at the action of R plus through, so this book by Folland on phase space has these formulas, and we have actions given by these integral formulas, actions on the Fock space actually. And using that, we get some kind of invariance on the symbols. Like we want the representation to commute with the Toplitz operators, and then we define the class of symbols using that. And so the problem was like, now we didn't get a group action on the class of symbols. So we made the representation commute with the Toplitz operators, and we got some kind of invariance on the symbols, but not through a group action, because so subgroups, so we get group action on the Fock space, but through these integral formulas, but not on the symbols. So, but we still get some kind of invariance. So I was actually wondering, is it really necessary to restrict the class of symbols through a group invariance?
Well, this is a very nice idea, because geometry says nice things.
Okay.
There is another form how you can extend your results. You know, your algebras are C star, but if you add invariant symbols called quasi-homogeneous, pseudo-homogeneous, and something like that, you will have still commutative algebra, but not C star, just Banach algebra.
Okay.
And in this Banach algebra, a bunch of questions appear, like describe the compact of maximal ideal, describe Gelfand transform. For many cases, this algebra will not be semi-simple, so you need to figure out what is the radical. So this somehow extension of the C-star result to Banach algebra result, passing from quasi-radial to quasi-radial, quasi-homogeneous, or something like that sort. There are many things already done in Bergman space case for unit ball. So you may look and think whether it's interesting for you.
Okay. Thank you.
Other observation, questions, suggestions? No. Thank you very much, Visva, for your nice talk. And who will next? Miguel, you're next.